Hello, this video is for Math 2415, Calculus 3, the solutions to the sample problems for Exam 2, Part 1. So let's start off with problem number 1, which is asking to find the first order partial derivatives of the given functions of x and y. So that means we will have a partial derivative with respect to x, and we'll have one with respect to y. So with respect to x, the derivative of x cubed will be 3x squared. Respect to x here, the multiplied y will stay with it because it behaves as a constant. So the derivative of 9x squared is 18x. So it makes it minus 18xy. And then for the last one, the y cubed will stay again as it's multiplied. And then the derivative of x is 1. So we have minus 2y cubed. So it takes care of that one. Now the same function with respect to y. The x cubed term has no y, so its derivative will be 0. And then the derivative of y with respect to y will be 1, so it would just leave a negative 9x squared. And then the derivative of y cubed would be 3y squared, which then makes that minus 6x y squared. Takes care of that one. Problem 2, same question. First order partial derivatives. And function of two variables is x over x plus y. So I'm going to use the old quotient rule from Calculus 1. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. So the bottom, the g, is x plus y. The derivative of the top with respect to x is 1 minus x, which the derivative of the bottom with respect to x would be 1 because just the x. And that actually simplifies a little bit. Oh no, of course the bottom squared. And you'll get a couple of x's that cancel in the numerator, so it simplifies to y over x plus y squared. And then the y partial will be x plus y times the derivative of the top of x with respect to y will be 0 minus x, and then the derivative of the bottom, x plus y with respect to y, will just be 1. And then that whole first part goes away over the same denominator. So you end up with minus x over x plus y squared. Number 3. To make this problem easier, anytime you have logarithms, and you properly use log properties. Yeah, you can't just make up properties that don't exist. With this one, I did two things. The log of a fraction is the same thing as the log of the numerator minus the log of the denominator, and then with logarithms allow you to bring the exponent down. So I just sort of changed the nature of the original function. You could have done it in its original form, but this is so much more easier right here once you have this. So the x partial, the 6 ln of y contains no x, so it'll be 0, and then the derivative of ln of x with respect to x will be 1 over x, so it's minus 9 over x. And then with respect to y, the derivative of ln of y will be 1 over y, so it's 6 over y. And then that second term, 9 ln of x, will be 0, so nothing goes there. So here are your two partial derivatives for that function. Number 4. Now this one is a function of x, y, and z. I just chose to use I brought the denominator up, and I'm going to use the chain rule here instead of the quotient rule. Theoretically, you certainly could have used the quotient rule here, that's no problem, but I chose to do it this way. And I suppose when you get to the answers, they're going to have positive exponents, and then it would be dropped down to the bottom. So what do we have here? So it's respect to x, y, and z. So respect to x, that multiplied z would be there. And then we'd bring the exponent down, negative 1/2. We would subtract 1 from that exponent, which makes negative 3/2. And then right here, this 1, that's the derivative of the inside. Remember the chain rule. With respect to x would be 1. Now the next one's very similar. The process is the same until you get to this last part. The derivative of the inside of the parentheses with respect to y squared would be 2y. Now that one I could have canceled the 2's out, obviously, but I just chose not to. And then the last one, you just take the derivative of z, which is 1, and all this other stuff, because it's multiplied to the z, it stays with it. So it's only when the variables are added or subtracted that you're not taking the derivative with respect to go to 0. But when they're multiplied, it would just be the same thing as if you had a 6 there or something like that. So the derivative of z is 1, so you're just left with x plus y squared to the negative 1/2. Number 5. Yeah, here I mentioned you also use the quotient rule, so I guess that could have been put in for number 4 also. But this one's is just so much easier to do it this way. It really, really is. So you bring up the x, becomes x to the negative 1. Bring up the z, and z negative 2. So you have x, z, and y. So that just means each partial derivative for x, y, and z, you're just focusing on the variable of interest, and the other two will sit there. So the derivative of x to the negative 1 would be negative 1 x to the negative 2, and the other two terms stay fixed. Now when you take the derivative with respect to y, the x and the z stay fixed. And so this time, yeah, and then the derivative of cosine of y is negative sine of y. So the negative in front of this fy partial is not there for the same reason that the 1 in the fx is. That one was because you brought the negative 1 down. This one is because the derivative of cosine is negative. So the last one, we leave the x and the y alone, and we focus on the z. So the derivative of z to the negative 2, you bring down the negative 2, which I just put out in front of the whole thing, and you subtract 1 from the exponent, so negative 2 minus 1 would be negative 3. Alright, like I said, I should have added right here in this little note about the quotient rule, but this way is much easier than I did. You know, I'm all for doing things the easiest way possible as long as it's mathematically correct. So here's a couple more. Let's take a look at this one. Function is xy e to the negative y. Now the partial derivative with respect to x is real easy because it'll just be the derivative of x is 1, so it just gets rid of the x. And you're left with y e to the negative y. Now the next one's a little trickier because since you have this y right here, and then you have e raised to the negative y, that means you have two functions of y multiplied together. The x just stays there. That means you have a product rule for this one. So I'll do I didn't write the product rule, but I always do it this is the way I do the product rule. I always go f. But there obviously there's two correct ways to do it. I always go f prime g plus f g prime, like that. But obviously you could go the other order first. So going in that order, the derivative of the x would sit there, and then y e to the negative y. If you're taking the derivative of the y, that's the f, and the e of the negative y would be the g. So the derivative of y would be 1. So that gives you x e to the negative y. And then here, the x, and so the x just sits there, of course. The f is the y, so it sits there. You have x and y. Then you take the derivative of e to the negative y. which will be negative e to the negative y, because the derivative of the exponent will be negative 1, so it brings down the negative, and then I just changed it to subtraction at the end. And then there we have it. Alright, so let's take a look at this is number 7. Yeah, it looks like this one looks sort of extra challenging here. Now, I sort of treated it as a sort of a substitution type thing here. Didn't have to do it this way, but I thought it made it a good way to do it. Is if you let u be sine of all this stuff in parentheses, then you can let z, your original function, is just the same thing as u squared. So all that right here, the original function, is now u squared, which means the x partial, you'd bring the 2, so it'd be 2u to the first, of course I didn't write the 1 there, times du dx, the derivative of this stuff with respect to x. And then for zy, it would be 2u du dy. So here's what u is. So there's, yeah, this one's quite the handful. So 2u, so both of these are going to share the same 2 sine of 3x y squared minus y. They both are going to share that. Now we're going to come over here, and this is going to be the du dx part right here. So the derivative of sine of anything, you know, I'd hate to say u, I've already got u there, we'll call it like sine of w, you know, it's a chain rule. So it'd be the cosine of w times the derivative of w. So in this case, it's the cosine of 3x squared minus y times the derivative of what's on the inside of this with respect to x. So the derivative of x is 1. You have 3y squared, and then this y would just, there's no x with it, so it would just be 0. So there's where the 3y squared is coming from right there at the end. And that's just kind of one big old mess there. There's nothing much to consolidate. But the only thing you really do is you could combine the 2 with the 3 and make 6. But that's probably not worth rewriting it. So now we take this same sine of 3x squared y minus y with derivative with respect to y. So it's still going to be cosine of 3xy squared minus y, but now the only difference is the derivative of the inside, we're taking it with respect to y now. So the derivative of y squared would be 2y, which makes it 6xy, and then the derivative minus y would be minus 1. And then just leave that big old mess right there. And that would be the answers for those two partial derivatives. Okay, number 8. Now we have second order partial derivatives. Of course, you can't get to the second without the first. So we have to do the first derivatives. So let's see what the fx will look like. And xy squared with respect to x would be 1, so it's just y squared. And then this one, the y would just sit there because it's multiplied, so the derivative of e to the x squared will be basically e to the u du. So it's e to the, I just put the du part in front. So it's e to the x squared, and then this 2x is the derivative of the x squared. So there's your fx partial. Now the fy partial, the derivative of xy squared would just be 2xy, because the derivative of y squared is 2y. And then this one, the derivative of y would be 1, so that just leaves you with e to the x squared. So that takes care of the partials. Now the second partials, there's 4 second partials, but remember you only have to evaluate 3 of them because the mixed partials are always equal to each other. fxy equals fyx, so it only has to be done once. So let's see what we have here. So the fxx partial. The derivative of y squared will be 0, so we don't see the y squared anymore. But now we have to take the derivative of this term. Since we have an x out here and we have an e to the x squared, we're going to have to do a product rule, since there's two different x functions multiplied together. So if we do the same thing, I won't rewrite that, but like I did before, I'm going f prime g order. In other words, f prime g plus f g prime. So the derivative, so that means my f will be x. So the derivative of x would just be 1. So you would just be left with 2y e to the x squared. Now, so the x will sit there because the f, now we're going to take the derivative of g. So 2xy sits there, and now we're just taking the derivative of e to the x squared. So the derivative of the x squared is 2x, and then just e to the x squared. And what did I do here? Oh, nothing fancy other than just kind of combine some loose terms here. 2x times 2x makes 4x squared. So that was just simplifying terms. Now the fyy would be the y partial of the y partial. So we look at this one. There's only one y term. The e to the x squared will just go to 0 because it's not multiplied by any function of y. So we have 2xy will be 2x. And that'd be it. So it's just 2x for that one. Now the mixed partial, since I wrote fxy, first, I'll go with that. Meaning, because like I said before, there's two ways to do it. I'll take the y. Let's see. The y partial of the x partial. So the derivative of y squared will be 2y plus the y partial of this will be derivative of y would just be 1. So that turned out not being too bad. And you're just left with 2x e to the x squared. So you don't have to, but that means if you took the fyx partial and actually figured it out, which you don't need to, we already got it, it would yield this same result because theorem says that they do equal each other every time. Number 9, substitution, chain rule type problem. Now in my notes, and I'm sure my lecture video over the same thing, the formulas for those chain rules are defined for you, they're given for you, but frankly, you don't really need to use them, and I'm not going to use them, and I don't think you have to use them, so don't worry about, I wouldn't even, worry about those formulas. Don't think you have to know them or anything like that, because you don't. Because substitution, frankly, works so much better. So you see we have a function w of x and y, and then x and y are both functions of t. And we're trying to find dw dt. So if you just substitute x in terms of t, y in terms of t, you'll then have a function only of variable t, then you can just take its derivative. In this case, we're actually plugging in a value. Sometimes you may plug in a value, sometimes you may not. Just depends on. So yeah, so I would just consider this approach all the time. This matches exactly the way I do it in my notes, and I'm sure I did in the video, of course. But so here's what we're going to do. So I'm evaluating w at cos t sine t, because x is cos, y is sine, and then you have, so x squared will be cos squared minus y is sine will be sine squared plus 10 cos of t. So when you take the derivative of that, now these are going to both be chain rules. Okay, so you would bring the 2 down, so it'd be 2 cos of t. It's like the derivative of u squared, 2u du. So 2 comes down, cos of t times the derivative of cos of t, which is minus sine t. And then for sine squared, same kind of idea. You bring the 2 down, so you have 2 sine of t. The derivative of sine of t is cos t. And then the derivative of plus 10 cos t will be minus 10 sine t. Okay. And then you have two like terms that combine together. A minus 2 cos t, a minus 2 sine t makes minus 4 sine t cos t. Another way you could do it, I wouldn't worry too much about it, but this, I just want to mention this just from a math standpoint, is cos of t, cos squared of t minus sine squared of t is actually this identity. It's cos of 2t. And the derivative of that would be negative 2 sine of 2t. And then sine of 2t is 2 sine t cos t. So negative 2 times that would give you this answer right here. It'd give you the same thing, but that's okay. I just thought I'd mention that. Not important. As long as you can do... Yeah, if it was something that was a huge savings of time for you, you know, I would have said, oh yeah, this is a lot faster if you do it this way, but this was not that bad. Oh, now this one's evaluated at a number, so we have to plug it in. So pi over 2. Cosine of pi over 2 is 0, so that wipes all that out. And sine of pi over 2 is 1, so you have 0 minus 10, which makes that negative 10. So dw dt at pi over 2 is negative 10. Number 10. So here's one where you have a chain rule problem, same idea, and I mentioned in the instructions. So now we have w in terms of x and y, and then now x and y are in terms of two variables. That's okay. Substitution still applies. That just means we'll have partial derivatives now, because the last problem, the function ended up being just w of t, single variable calculus, so we didn't have to use partial derivatives. But now w will be a function of u and v. So let's just substitute, put a u minus v in there for x, and we'll get u minus v here. Y is uv minus u times v squared. And looks like I went ahead and just distributed this out, made it a little easier. So u times uv would be u squared v, minus v times uv is minus uv squared. And that gives you minus u squared v squared when you square these terms. So the partial respect to u. Oh, this was only asking the partial respect to u, but you know what? I might just verbally run through what the partial respect to v is. So I won't write it, but I'll just say it, you know, and walk you through it. But this was only asking for respect to u, so the derivative of u squared v respect to u would be 2uv, and then the derivative of u is 1, so you'd have minus v squared here. And then the last one, the derivative of u squared would be 2u, so it's minus 2uv squared. So now you put in 1 for u, 4 for v. So here we have 2 times 1 times 4, minus 4 squared, minus 2 times 1 times 4 squared. I believe that'll be negative 40. But anyway, let me just say this verbally. So the derivative of this function, the partial respect to v would be 1, so it'd be u squared, and then minus 2uv, because the derivative of v squared would be 2uv, or 2 would be 2v, and then the u makes it 2uv, and then the derivative of v squared would be 2v again, so it'd be minus 2u squared v for the last term. Okay, just thought I'd mention that. Implicit differentiation. Okay, let's take a look at this. So you're definitely going to make sure you have the formula for that one. That's not too difficult though. And it's just negative of the fx, the f partial respect to x, and then divided by the fy, so the f partial respect to y. So it's also at a point again too, okay, which it certainly didn't have to be. We could have just been asking for it, you know, in variable form. So the derivative of this with respect to x, 3x squared will be 6x. 2y cubed, there's no x term there, so that'll be 0. Plus 2xy makes that 2y. And then over here we have no y term for the first one, so that will be 0. 2y cubed will be 6y squared. And then plus 2xy will be, the derivative of y would be 1. So it'll be 2x. So the capital F means these are kind of written in implicit form. So what that means is implicit form is if you have variables on both sides, you got to get the variables all over on one side. We'll see that in later problems in this review, and you've probably already seen it in the notes by now, is on the tangent plane problems or whatever. So the capital F just means it needs, all the variables need to be together in implicit form. It wouldn't matter if there was just a number other than 0. That doesn't matter because the derivative of it would be 0 anyway. So you just take, so you have to take the negative of 6x plus 2y over the fy, which is 6y squared plus 2x. And you could distribute the negative, but I just plug the numbers in first. They're both 1s, so it makes it 6 plus 2 will be 8, so it makes it negative 8. And then 6 plus 2 on bottom, of course, is positive 8, so we have negative 8 divided by 8, which is negative 1. So now we have a zx and a zy partial. And this, so in other words, this is implicit differentiation for multivariables for this particular question. The last one was just single y in terms of x. This one's z in terms of x and y, but it's in an implicit form, so we have to use this rule to get the partial derivatives, because you can't isolate z. There's no way you could isolate z out of this equation. Alright, so let's see what I did here. I just okay, I don't know why I wrote that all out again. Oh, I see what I did. I thought that was not okay. Now, yeah, I did. That did accomplish something. Used a log property. And once again, as I mentioned earlier, I like to use log properties whenever they apply. So the log of a product is the same thing as the sum of the logs. So ln of xz, x times z, is the same thing as ln of x plus ln of z. And of course the 4 distributes to both of those. So here are the formulas you need. It's the negative of fx over fz for the zx partial. For the zy partial, it's negative fy over fz. So these both these answers have the exact same denominator. So let's look at this function then. The derivative with respect to x, negative 6x squared will be negative 12x. 4 ln of x will be 4 over x. None of the remaining terms have an x. They have no x, so they're all 0. Now we have partial of f respect to y. So the first 3 terms do not have a y, and neither does the last term. So we only have to focus on this one term, negative 2y squared, 2yz squared, excuse me. And then the derivative of y would just be 1, so it makes it negative 2z squared. So that's all we have here. And then the last one, for respect to z, the first 2 terms do not have a z, but the last 3 terms all have a z. So we'll have to take the partial of those last 3 terms. Let's see what we have here. 4 ln of z, the derivative of ln of z will be 1 over z. So it's 4 over z. And the derivative of z squared will be 2z, so it makes it negative 4yz. And the derivative of e to the z, now it's just z, so that, you don't have to worry about the chain rule. In other words, well, the derivative of z is 1, but, obviously, if that was if it was e to the z squared or something, you'd have a 2z in there. But so the derivative of negative 7e to the z would just be negative 7e to the z. So here's your common denominator between the two. So here you see the answers right here. There's the denominator. And then for the zx partial, that means the negative of this goes on the numerator. So that makes this positive and that negative. So it's positive 12x minus 4 over x. And then for this one, it's negative fy, so the negative of negative 2z squared would be positive 2z squared. There we go. Number 13, the gradient. So gradient's a vector, and its components, in this case for 3 variables, will be fx, fy, fz. So this one shouldn't be too bad. The x partial, the derivative of x is 1, so it'll just be remaining negative 2 y cubed z squared. The next one will be the derivative of y cubed will be 3y squared, so it makes it negative 6xy squared z squared. And then z squared would be 2z, so it makes it to negative 2 makes that negative 4, so then you have xy cubed z. So once you get those 3 partials, they're giving us a point here, and then all I did was plug in. Okay, that's what. Yeah, numbers are a little large here, but that's why we're using calculators. So I'm not too concerned. If we weren't using calculators, I'd be concerned about that. So okay, I won't go through all the steps here, but you're just literally plugging in these numbers for x, y, and z into that vector, and you get these 3 vector components right here. Okay, so as long as you get the partial derivatives correct, even when you plug in numbers, gradients, easy enough. Now we want to find a unit vector which is normal to the surface with the equation z equals x squared plus y squared. Now geometrically, that's one of the things that what the gradient vector does. It gives you a normal vector at a point on a 3-dimensional surface. It will give you the normal vector sticking away from that point at that surface. So it automatically, by definition, the gradient's giving you the normal vector. However, the question is asking unit vector. So you calculate the gradient, but we have to convert it to a unit vector, just like way earlier in the course. To convert something to a unit vector, you divide it by its magnitude. So always be careful to see if the problem's expressing just, if it says find a vector which is normal to the surface, blah blah blah, and it doesn't say unit, you just do the gradient and that's it. That would be the answer. But that's what this normalize is the term they use for converting something to a unit vector. Now, to put this in implicit form, capital F, what you have to do is, it works, even though this function's not implicit, this works so much better if you make it implicit. It's easier to deal with. So I'm intentionally moving that z over to the other side, making it negative, and we're calling that just big F right there. But technically, z does equal little f of xy, which is x squared plus y squared. We're going to move the z over and make it implicit looking here, because it's so easy. It's easier to take. You can do it without it doing that, but it's so much easier to do it this way. Which means for when it's explicit like this, that means this last component's always going to be negative 1. Yeah, but that's okay. So partial's easy. You get 2x, 2y, negative 1. So there's your gradient vector in terms of x, y, and z. And then now we plug what point to give us that normal vector at that point. 1, 1, 2. So you get 2, 2, negative 1. So that is your normal vector. But the gradient of that, the magnitude of that gradient, I didn't write it out, but it's easy. is, so you're evaluating 2, 2, 1, so it's 2 squared is 4, 2 squared is 4, negative 1 squared is 1, 4 plus 1 is 9, square root of 9 is 3, so I didn't show that, so I figured, I'm sure you're pretty good at calculating magnitudes by now. So it's 3, so we have to take the components of this answer and then just divide everything by 3, therefore to make a unit vector. So it'd be 2/3, 2/3, negative 1/3. All right, that's all there is to that one. This one, number 15, directional derivative. That will be the dot product of the gradient times the direction vector as a unit vector. That's very important. The direction vector must always be converted to a unit vector for this formula to work. Not that that's hard to do, you just have to remember to do it. So the gradient, this function is pretty easy. I think it's not too bad. So 2xy will be 2y, x will be 1, minus xz, which will be z. The last term has no x. We go to the middle one. First term, the derivative of y is 1, so it's 2x. Middle term has no y. And the last term, 3yz, would just be 3z. First one, no z's, you could ignore it. Negative xz, derivative of z is 1, so it's negative x, plus 3y. All right. And then the point is 1, 1, 1. So if you put 1, 1, 1 into these vector components, you'll get the vector, the gradient vector of 1, 5, 2. And then the magnitude, now we don't want the magnitude of this gradient vector in this case like we did the last problem, but that was asking a different question. So that you're taking the magnitude of the direction vector to negative 1, 1, so that when you square that, it'll be 4 plus 1 plus 1, so you have the square root of 6. So now you just take this direction vector of 2, negative 1, 1, you're essentially dividing it by the square root of 6. And I could distribute that, but you could actually leave it right here, because when you take the dot product, you can just multiply the integer values, and then we're definitely going to have the 1 over square root of 6 as part of the answer. In other words, 1 times 2 is 2, 5 times negative 1 is negative 5, so that makes it negative 3. 2 times 1 is 2, that makes that negative 1, but it's still all multiplied by 1 over root 6. So it becomes negative 1 over root 6, which is correct. Or if the answer is rationalized, that's the same thing as saying negative square root of 6 over 6. All right, directional derivatives, not too bad. Here's another one. We have the partials are going to be 12x for fx, and then fy will be negative 3. So the gradient at negative, the given point, negative 6, 7. So 12 times negative 6 will be negative 72, and this is fixed at negative 3, so it just stays negative 3. And we have to convert this to unit vector. I didn't write it out here, but the magnitude is 5. Well, I wrote it right here, but I didn't show the magnitude. The magnitude is 5. It's the square root of 9 plus 16, the square root of 25. So the converted to a unit vector, it'll be 3 over 5, comma, negative 4 over 5. So we just dot product that with, oh, there's a dot product form, and there's a directional derivative formula. I didn't have that in the last problem, but there it is. So easy, you just dot product here, easy. And they end up with negative 204 divided by 5. Okay, number 17. Now this one, notice it's a 3-variable problem. And notice the vector, so it's a little bit different. The last one was just x and y, that was okay. So what you do on this kind of problem is you just treat it, it is still considered 3-dimensional, but you just treat that as 0k. So the third component of that vector, so if it's written in component form, it would be like this, it would be 3, 4, yuck, 0. So you just tack on a 0. We didn't do that in the last problem because it was only in terms of x and y. So no problem. We just tack on a 0 there and we're good to go. And then the magnitude would still be 5, actually. So your unit vector would just be 3 over 5, 4 over 5, 0. Partial derivatives. The derivative of the natural log of something is the derivative of the inside over that inside. So you see what's on the inside here, all that stuff is the denominator for every one of these. And the numerator is the derivative with respect to whatever variable. So for fx, it'll be the derivative of x squared, which is 2x. For fy, it'll be the derivative of negative 5y squared, which is negative 10y. And then for negative 2z squared, it'll be negative 4z. And then there we go. So those three now, we the value points negative 5, negative 5, negative 5. So you just put the plug in negative 5 for every variable in here. And I got negative 10 over negative 150, 50 over negative 150, and then negative 20 over negative 150. Which you could certainly, right off the bat, is you could get rid of the zeros and reduce this. I didn't here, but what I did do, I didn't actually, because they're kind of not next to each other. But oh yeah, so you take the first one, negative 10 over negative 150 times 3 over 5. 50 over negative 150 times 4 over 5. The last one's 0. That doesn't matter. So dot product both these vectors in blue will lead you to 170 over negative 750. Okay, I just fixed that typo I saw there where I had negative 17 over 15. And then actually it's negative 17 over 75. So that was just a handwritten mistake on my part. But I do have the answer correct right up here. So, okay, that's all fixed. So it's negative 17 over 75.